Drag you over there. Okay, so welcome to Crafting Interpreters in Rust. We just got finished, well, nearly finished with the parser stage of the process. So now we are finally ready to start reading the book again, after like months of just parsers and macros and stuff. Um, so I was gonna recap what we have read and what we've implemented pretty quickly, and then we can read chapter 7. Um, so to recap what the book is and what we're doing with it, that we're doing the book describes how to implement a language called LOX. LOX is a pretty minimal dynamically typed language, sort of like Python. Um, the first stage of the book, which is what we're still in, is how to make a tree walk interpreter, what's called a tree walk interpreter. Um, and what the reason it's called that is because you take the code, you construct an abstract syntax tree, and then in order to execute the code, you traverse over the tree, doing the appropriate thing when you visit each node. Um, so it's a very straightforward approach. It's kind of suboptimal because it involves keeping this big in-memory data structure whenever you're doing anything. The second stage of the book is making a one that's supposed to be faster by making it use bytecode instead of directly going over the AST. That's similar to what CPython does for Python. And because this is the Rust meetup, we're doing both of them in Rust instead of the first one being in Java, the second one being in C. And there's a slight advantage to that, which is that we get to reuse a lot of the Java parsing code for the second interpreter. All right, so what we have read so far are the first 6 chapters of the book, introducing the structure of the book and a thorough description of what the LOX language looks like. And then the first few steps in writing the interpreter. So the first one is taking raw text and turning it into chunks that the parser is willing to accept. This is called scanning or lexing. We implemented the scanner pretty fast. 5 was about how to structure things as an abstract syntax tree, and it also talked a lot about the visitor pattern, which is a way to, in Java, to iterate over the nodes in an abstract syntax tree. And then finally, we got to the parsing bit in chapter 6. And the method of parsing that it describes, it acknowledges all the whole like compiler literature on LR parsing and LALR, whatever, all those things that you talked about in compilers class. But the way that it actually does it is called recursive descent, and it's very simple. And we use the same method in the Rust version. So here's what we have done. I put a link to the repository where we're doing this stuff. We got the scanner. Chapter 6 described the sort of as an illustrative example, how to do parsing for basic arithmetic expressions. So we did that first. And then we went off on a crazy tangent trying to make a macro to accelerate the process of parsing the full grammar. And then the next part of the book is chapter 7, which is about evaluating expressions, like so actually visiting the stuff in the abstract syntax tree and doing stuff with it. We haven't touched that at all, so that's what we will do next. So because we're doing this in Rust, we have some different choices to make from the book's implementation. I'm going to go over some of the obvious differences here. So we don't have classes. Java's all about classes, but Rust doesn't have them. So, but you can get a similar interface by making a struct and then making an impl block. In an impl block, you can define functions operating on the struct, and then Rust lets you use method syntax. So, foo.bar to call the method. So roughly equivalent. Rust has enums, which mean, or some types, which means you can declare a type that is one of several options. So, if you make a struct that says, like, a classic example, struct vector, which is an X, which is a float, and Y, which is a float. The struct is a composite data type, which is X and Y. And then by contrast, an enum is, let's see, I don't know what a good, it's like, it's or instead of and. It can be X, which is a string, or Y, which is a float. So that allows you, and what that actually means is that at runtime, it's going to keep track of which enum variant it is. So it has like a little tag that says, oh, I'm the variant called X, which is an int, or I'm the variant called Y, which is a string. So, and that's what an enum is. And it turns out this is a very good choice for encoding the tokens. Let's see. Yeah, tagged union. Tagged union is a language agnostic name for this sort of thing. So we have like one enum variant per type of token that you can emit. And then the variants can contain different data formats. So, most of them are just a marker to say, oh, you got the keyword or you got the keyword this, or whatever it is. But then some of them are like, you have a number literal, and here is the value of the number literal. So we modeled token type as one big enum. In addition, Rust has a pretty fully featured macro system. So we used it to write a thing that takes a grammar rule in a syntax similar to the grammar rules in the book, and then outputs the code for parsing it using the method that the book describes, which is recursive descent. So I will go over that because that's sort of the wildest part of what we've done. In chapter 5, the book has this whole tangent on, you write one Java file that produces another Java file, and the other Java file is the boilerplate code that you need for the visitor pattern. So far, we have not had any reason to use the visitor pattern because we are not visiting nodes yet. So, we have the code to construct the tree, but we don't have anything that we need to do with the tree yet. That's what we're about to get to. And that means we haven't addressed this problem of how do you visit the nodes. I guess we can fall back on this, but this is a very object-oriented way of doing it, the visitor pattern. So we will see if Rust has a smarter thing. I don't know yet. All right, so I was going to just go show the code for at different stages of completion. So here we go. So here is the code at the point that we were finished with the Lexer, according to GitHub. So here's the here. Let me find the enum thing I was talking about. So here's a big enum. You can see here are all the token types. So to be clear, this is a Lexer token, which means you have a sequence of raw characters in the text, and now you want to collapse it to one semantic thing for the language. So, that can be a left paren, right paren, some literal symbols, but it can also be a sequence of characters. For example, an exclamation mark can mean either negation or the not equal operator. So those are semantically different, so we want to encode them as two different tokens. And in addition, it can also be one of these special types of tokens which has a value in it that you need to keep track of. So if you have a string literal, like hello world, you need to keep track of this string somewhere. If you have a 5.0, you need to keep track of this. And if you have, foo, which is some variable, you need to keep track of the name foo in your tree. All right, so that is what we're encoding. And the goal of the lexer is to take some text and then turn it into a sequence of these things. Except not just these. We want to encode what type of token it was, the lexeme, which is the compiler word for where the code came from, or well, where the original characters were that became that token, and what line it was on, and we need to track what line it was on for compiler errors. If you mess something up, it's useful for the compiler to say unexpected token on line whatever. So let's see what our tests do. We have some tests. Yeah. So here's some sample code. It's not a very good program, but it should lex at least. So the interface is scanner new, and then you iterate over the scanner by collecting the tokens into just a vector. And then the tokens should equal this sequence of things. So this was to test that when you provide things like 3 and 35.3, they get parsed out correctly as numbers. And so on. There's yeah. The logic to do this is not very complicated. There's a few places where you have to use look ahead and stuff to figure out how many characters you should consume to produce the token. But yeah, it's straightforward, just like the book. All right. So let's see. The next thing I was going to talk about is the expression parser. So let's fast forward. What are the new tests that we had? Yeah. So here's ones that are supposed to throw an error. Yeah. So the next stage is turning the lexer tokens that are output from the lexer or scanner into a syntax tree. And among other things, you need to handle precedence at this point. So here's our sequence of characters. You can see we do the same thing where we turn it into a bunch of tokens, and then we try to parse it as an expression. So expression has a method parse, static function parse, really. It takes some tokens, and then we say this should equal an expression, a binary expression, whose left side is another binary expression, which is 3 times 4. And then that whole thing should be multiplied with the right side, which is just the 5. So this is also where we needed to handle some error cases, such as this. If you have like unbalanced parentheses, it should tell you that, and so on and so forth. So I'll see if I can go over this is sort of what the book directly told you to do in chapter 6, is parsing these. So in fact, let me bring up the relevant section of the book. Yeah, here we go. Maybe, wait. Yeah. There we go. This is what I was looking at. Yeah. So there will be a correspondence between how this code looks and what the grammar tells you to do. So the grammar is the description of how like the tokens are supposed to be organized in the language. And it's there's like sort of a common format for languages to have a grammar that looks like this. The basic way it works is that you have these expressions at different levels, and they're composed of other expressions, sub-expressions. So an equality is some other expression, which is called a comparison, joined with any number of other comparisons by one of these two tokens. And that's just as an example. So actually, I'll go down here for the most basic example. So for a primary, which is just sort of like an elemental expression, there is it can be one of a number of things. It can be a number, it can be a string, it can be one of these literals, or it can be a parenthesized entire other expression, because you want to completely parse anything in parentheses before you try to parse anything above it. So to go over how this turns into code, here are all the basic cases, right? If you have a number, then you return that it's a number. If you have a string, you return that it's a string, and so on. If it's none of the expected things, then you say, I didn't unexpect a token. So that's where you start doing an error. And then finally, here's the parenthesized case. If you have a left paren, then you try to parse until you have a right paren. So here's the recursive descent part. You try to recurse another expression. This self here is expression. So you recurse another expression out of the remaining tokens after the parenthesis. That gives you back some more tokens to say like, okay, here's the expression that I thought I got out of the rest of the tokens. And then you look at the one right after that, and that had better be the right paren, because it should parse all the way to the end of the expression. If it's not the right paren, then you're missing one. Otherwise, you return this is grouping indicates that it's a parenthesized expression. So that's really all that recursive descent means, is that when you come when you encounter a case where you have to go parse something else, you literally just call the function to go parse that something else. And we can go see. So going up sort of the layer of how this is organized a little bit. The next layer is a unary expression, which means it's either a negated unary expression. These are the two things that you can put in front of a unary expression, or it's just a regular primary expression. So in order to parse it, we have this try from thing. The try from just means like, is it one of these two tokens? If it is, then we try to parse, we like, keep track of which one it was. And then we try to parse another unary out of the rest of the tokens. Otherwise, where in this case, we try to parse a primary out of all of the tokens. So there you go. It's recursive descent. All of the other stuff follows the same pattern. So here is where we first ventured into macros. What we noticed is that all of the other ones here are all follow the same format. So it's always like this thing is composed of a bunch of these things separated by some set of tokens. So we tried to sort of abstract that pattern away a little bit, save ourselves from writing the same boring parsing code over and over. That's foreshadowing. So here is the here's the macro to do that. It's actually two macros. One of them outputs takes like, you know, the name of the thing and the name the thing is composed of. And then a function for figuring out if if there's another, like, one of the valid tokens that these are separated by. That's what that means. And then the code for parsing them is always the same. It just sort of like matches the structure of how this is organized. So the star means there's any number of them. So you have to keep parsing, you know, in a loop until you sort of run out of them. So to long story short, that's when we call that, let's see, where did it go? Yeah, this is why we need to organize the code. Yeah.
I was just curious, what's the benefit of like the macro over like a generic function or something that you could reuse?
It's because what we want to change is we want to generate the names of these functions is the thing. So what we end up with is a function called parse equality, which then you can go, so that's made at compile time using the macro. And then you can just go call it at runtime instead of having to do parse and know how to pass in to say, like, pass in, I want to parse an equality thing instead of, you know, whatever else.
One big problem with using generics is that if you look at the cases, we have cases that take 3 parameters, we have cases that takes 2 parameters. Variadic generics are not yet even implemented for Rust. So we ended up using macro.
Cool. I was just curious. Thank you.
I have a question.
Yeah.
All of this macro expansion magic happens at compile time. Do you get to see the result of do you get to see what the functions that would have been made if
Yes, we do.
in the original way?
Yes, we do. And I can do that. In fact, that's how you need to debug macros, because as you might imagine, you can get some weird generated code. You have this thing called cargo expand. It prints out, once it's finished thinking about my code, it prints out the macro expanded version of the code. So I'm going to pipe this into a file and open the file. And then we can look at it. So in fact, there's actually a lot of things Rust is doing behind the scenes at compile time all the time. For example, by default, it will import the standard library. But you don't have to explicitly do that. It just puts it at the beginning of your program because it's like, but implicitly. And then anytime that we used the derive thing, so if you want to derive a trait on one of your types, you can use this #derive thing. And the implementations for those traits are expanded by macros. So if you want to see what it means to derive debug for lock syntax error, this is what the code actually is. So to go over to our stuff, here, yeah, here they are. Here's what the resulting functions are that are printed out by the macro calls.
And
then
they
we can,
look like what you would have written if you were just slavishly following the Java version of the book.
yes.
That's cool.
So to go, yeah, here's the macro. You can see the code sort of bears a resemblance to what's generated. And then here is where we call, here's the code that we actually write instead of the parsing function. So this line here becomes this function here. Right. So that's the Rust macro basics. Then we went off the deep end of macros, I would say. So all we've gotten here is mathematical expressions, right? This grammar just tells you how to parse, you know, 3 times 4 times 5, or you know, stuff like this. You know, -2, whatever it is. Yeah, mathematical expressions. It's not a language. It's not, well, it's not the LOX language. So the entire LOX grammar is here. So at the top level, a program becomes any number of declarations, and then the end of file marker. And then we have what a declaration means. It can be any one of these things. And then we have what a statement means. It can be any one of these things. So if you can imagine, so if you look at how much code we had to write just for mathematical expressions, you can imagine how many lines of code it would be to do that same handwritten thing for the full grammar. And then if you want to change the grammar, if you want to slightly change your syntax, that's, you know, you have to reach into one of those many functions. So the dream would be that we just copy paste this grammar, and then we have some process we run to output the code for parsing it. So that's a parser generator. Those do exist. They're commonly used in compilers. Let's see, I forgot what the one that we used in the compilers class that I took was, but yeah, they all have cute names, like yet another compiler, and this is a parser generator. So it takes a grammar file in a format similar to this, and then it outputs code for parsing it. And I don't exactly know what language it targets, or if it makes just like an executable or what.
Yes, I think it makes a C library.
A C library, okay. Yeah.
So it makes a whole bunch of ugly, horrible C functions that you don't ever want to read.
Correct.
But you are glad you didn't have to write.
Yes. So we tried to do something like that, but in the Rust macro system, which I thought was sort of ambitious, but we kind of did it. So let me check out. Oops. All right. So you'll notice that macro that we had before has been replaced with this slightly longer macro called grammar rule. Grammar rule, here's where we actually use it. So I've sort of stated this a couple times in the recording, so I don't want to really go into this whole spiel again. But here's roughly where the original grammar rule from the book goes. But you need to change a few things around. So this will generate a parser function called print statement. And we're just following the names from the book here, or what types of statement there are. And this is the pattern for it. So you'll notice that instead of the literal word print, like what was in the book, we have the name for our token, the Lexer token print, and so on. Then when we need to do recursive descent and parse another thing, we came up with the syntax to put square brackets around it. So this means go and parse a sub-expression, which is an expression. And so on. Then what the macro produces is a big jumble of recursive nonsense, which we have to make sense of and turn it into an AST node. So going back to enums, we had an enum for all the Lexer tokens, and now we have enums for all the abstract syntax tree nodes as well. So an expression can be one of these things. It might contain this data like this. Declaration can be one of these things. A statement can be one of these things. And I think that these are missing data, so we have to flesh that out. So this part handles recursing, or the like parsing into a bunch of recursive nonsense, and then we have to supply a function which turns the recursive nonsense into a node in the AST. So we still have to make all these builder functions. You can see unimplemented. We have one, or we have a few. So you can see sort of what they look like. So here is the data, which is just a blob of crap that the macro gave us. And the structure of this blob is dependent on how we write the macro. And then we need to make it into a nice orderly AST node like this. So we will have to do, there's still some drudgery, right? Because even though we have this nice macro that does the parsing for us, we still have to make sense of the data. But this, with all the tests and everything, is like 1,000 lines of code. And if I do cargo expand at this point, and open it up, you can see I'm going to quickly scrolling past the ugliness that the macro generates. So here's some ugliness. And then at the end of it, it's 3,000 lines of code. So the macro calls collectively constitute 2,000 lines of code that we saved. Okay. This sort of explanation went on longer than I thought it would. I guess I went into more detail, but all right. And then there's another issue we have to sort out with the macro, and we'll take care of it. Because we kind of want to move on with the book. This is a whole rabbit hole, but we're almost there. We just need a few annoying pieces to get it working. So questions at this point. I can go into detail on the macro if you want, or anything else. Yeah. Right. Okay, in that case, we can get started with chapter 7. So I'll just start reading chapter 7 of the book. After like months on chapter 6 and in our world of this one macro, we can continue. All right. So chapter 7 on evaluating expressions. If you want to properly set the mood for this chapter, try to conjure up a thunderstorm, one of those swirling tempests that likes to yank open shutters at the climax of the story. Maybe toss in a few bolts of lightning. In this chapter, our interpreter will take breath, open his eyes, and execute some code. There are all manner of ways that language implementations make a computer do what the user's source code commands. They can compile it to machine code, translate it to a high-level language, or reduce it to some bytecode format for a virtual machine to run. For our first interpreter, though, we are going to take the simplest, shortest path and execute the syntax tree itself. Right now, our parser only supports expressions. So to execute code, we will evaluate an expression and produce a value. For each kind of expression syntax we can parse, literal, operator, etc., we produce a corresponding chunk of code that knows how to evaluate that tree and produce a result. That raises two questions. What kinds of values do we produce? And how do we organize those chunks of code? Taking them on one at a time, representing values. In LOX, values are created by literals, computed by expressions, and stored in variables. The user sees these as LOX objects, but they are implemented in the underlying language our interpreter is written in. That means bridging the lands of LOX's dynamic typing and Java's static types. A variable in LOX can store a value of any LOX type, and we can even store values of different types at different points in time. What Java type might we use to represent that? Given a Java variable with that static type, we must also be able to determine what kind of value it holds at runtime. When the interpreter executes a plus operator, it needs to tell if it is adding two numbers or concatenating two strings. Is there a Java type that can hold numbers, strings, booleans, and more? Is there one that can tell us what its runtime type is? There is. Good old java.lang.object. In places in the interpreter where we need to store a LOX value, we can use object as the type. Java has boxed versions of its primitive types that are all subclass object, so we can use those for LOX's built-in types. So anything is an object, nil maps to Java's null, and so on and so on. Given a value of static type object, we can determine if the runtime value is a number or a string or whatever using Java's built-in instance of operator. Okay, so we're runtime casting. In other words, the JVM's own object representation conveniently gives us everything we need to implement LOX's built-in types. We'll have to do a little more work later when we add LOX's notions of functions, classes, and instances, but object and the boxed primitive classes are sufficient for the types we need right now. Evaluating expressions. Next, we need blobs of code to implement the evaluation logic for each kind of expression we can parse. We could stuff that code into the syntax tree classes in something like an interpret method. In effect, we could tell each syntax tree node, interpret thyself. This is the Gang of Fours interpreter design pattern. The Gang of Four is a reference to the design patterns book, the authors of that. It's a neat pattern, but like I mentioned earlier, it gets messy if we jam all sorts of logic into the tree classes. Instead, we're going to reuse our groovy visitor pattern. In the previous chapter, we created an AST printer class. It took in a syntax tree and recursively traversed it, building up a string, which it ultimately returned. That's almost exactly what a real interpreter does, except instead of concatenating strings, it computes values. We start with a new class. All right, so the interpreter is a visitor. There's a subclass of visitor. The class declares that it's a visitor. The return type of the visit methods will be object, the root class that we use to refer to a LOX value in our Java code. To satisfy the visitor interface, we need to define visit methods for each of the four expression tree classes our parser produces. We'll start with the simplest. So evaluating literals. The leaves of an expression tree, the atomic bits of syntax that all other expressions are composed of, are literals. Literals are almost values already, but the distinction is important. A literal is a bit of syntax that produces a value. Yeah. So a literal always appears somewhere in the user's source code. Lots of values are produced by computation and don't exist anywhere in the code itself. Those aren't literals. A literal comes from the parser's domain. Values are an interpreter concept, part of the runtime's world. So, much like we converted a literal token into a literal syntax tree node in the parser, now we convert the literal tree node into a runtime value. That turns out to be trivial. You just return the value. We eagerly produced the runtime value way back during scanning and stuffed it in the token. The parser took that value and stuck it in the literal tree node. So to evaluate a literal, we simply pull it back out. The next simplest code to evaluate is grouping. The node you get as a result of using explicit parentheses in an expression. Yeah. So if when you visit a grouping, the result should be the same result as just evaluating the grouping. That's what that's saying. A grouping node has a reference to an inner node for the expression contained inside the parentheses. To evaluate the grouping expression itself, we recursively evaluate that subexpression and return it. We rely on this helper method, which simply sends the expression back into the interpreter's visitor implementation. Okay, yeah, so this is some visitor pattern stuff. Okay. Like grouping, unary expressions have a single subexpression that we must evaluate first. The difference is that the unary expression itself does a little work afterward. Okay. Let's see what this means. So a unary expression in their organization has like the operator, which is the minus or bang, and then a dot right, which is the subexpression. First, we evaluate the operand expression. Then we apply the unary operator itself to the result of that. There are two different unary expressions identified by the type of the operator token. Wait, where is it actually applying the negation? So if it's a minus, it's that, but what if it's a bang? Oh, okay. It just didn't add it. Okay, yeah. First, we evaluate the operand expression. Then we apply the unary operator itself to the result of that. There are two different unary expressions identified by the type of the operator token. Shown here is minus, which negates the result of the subexpression. Subexpression must be a number. Since we don't statically know that in Java, we cast it before performing the operation. This typecast happens at runtime when the minus is evaluated. That's the core of what makes a language dynamically typed right there. You can start to see how evaluation recursively traverses the tree. We can't evaluate the unary operator itself until after we evaluate its operand subexpression. That means our interpreter is doing a post-order traversal. Each node evaluates its children before doing its own work. The other unary operator is logical not. The implementation is simple, but what is this truthy thing about? We need to take a little side trip to one of the great questions of Western philosophy. What is truth? Okay, maybe we're not going to really get into the universal question, but at least inside the world of locks, we need to decide what happens when you use something other than true or false in a logic operation, like not, or any other place where a Boolean is expected. We could just say, yeah.
I have a question.
Yeah.
Back in the minus case where the thing that it's minusing is supposed to be a number.
Yeah.
The way that they handle it is just cast it in Java to a double. But what if it isn't a number? What if it's a string or something? Is it going to?
It will pop up Java's error.
Is it? Will it just
yeah.
So if it's a variable,
unless you wrap it in a locks error to handle this,
okay,
it will return the same error as Java for not being able to cast, I believe. Yeah, and the reason that might happen is because we're working with generic Java objects here. And then we're doing a runtime cast to double. So yeah, this Java object could be not a double. Yeah. Okay, so we could just say it's an error because we don't roll with implicit conversions, but most dynamically typed languages aren't that aesthetic. Instead, they take the universal values of all types and partition them into two sets, one of which they define to be true or truthful or truthy, and the rest which are false or falsy. This partitioning is somewhat arbitrary and gets weird in a few languages. Locks follows Ruby's simple rule. False and nil are falsy, and everything else is truthy. We implement that like so. So is truthy of an object? If it's null, then it's false. If it's a Boolean, then you use the Boolean value, otherwise it's true.
Oh, so this is not the C or Perl version of like 0 is false and 1 is true.
Yeah,
This is okay. This is not that.
yeah. They did that because they didn't, for some reason, they wanted to reuse integers as Booleans in C. Okay. Evaluating binary operators. On to the last expression tree class, binary operators. There's a handful of them, and we'll start with the arithmetic ones. So, yeah, again, post order. You evaluate the children, and then you apply what the operator is supposed to do to the results. And then do the dynamic cast at this point. I think you can figure out what's going on here. The main difference from the unary negation operator is that we have two operands to evaluate. I left out one arithmetic operator because it's a little special. Right, so the plus might like mean two different things depending on whether you're adding numbers or concatenating strings. And so the language figures out which one to do based off the runtime cast that you can do here. Yeah, the plus yeah, he says the same thing. Yeah, we don't just assume the operands are a certain type. We dynamically check the type and choose the appropriate operation. This is why we need our object representation to support instance of.
Right, but then if it isn't either of those two, then it just hits a break statement. Well, then what does it do?
Good question.
Like if I'm not adding two numbers and I'm also not concatenating two strings, if I'm adding a number to a string, then it just like ducks out of here and doesn't actually return anything?
That's what it looks like so far. Maybe he's not addressing the question of what errors to return for now. He's just, this is happy path. Gonna see if, yeah.
Well, return it exits the function, break exit the switch statement. I'm assuming somewhere at the end it generates the error message. Shit happened.
Oh, but you didn't say shit happened here. You just didn't do anything,
Not yet.
right? Yeah.
I think it's going to be after the switch.
Yeah. All right. Next up are the comparison operators. So additional cases. They're basically the same as arithmetic. The only difference is that where the arithmetic operators produce a value whose type is the same as the operands, the comparison operators always produce a Boolean. The last pair of operators are equality. All right, need another helper function for this. Unlike the comparison operators, which require numbers, the equality operators support operands of any type, even mixed ones. You can't ask LOX if 3 is less than the string 3, but you can ask if it's equal to it. Like truthiness, the equality logic is hoisted out into a separate method. So are these two objects equal? If they are both null, return true. If only one of them is null, return false. Otherwise, use Java's equals. Okay, that's a strong choice. This is one of those corners where the details of how we represent LOX objects in terms of Java matter. We need to correctly implement LOX's notion of equality, which may be different from Java's. Fortunately, the two are pretty similar. LOX doesn't do implicit conversions in equality, and Java does not either. So we do have to handle nil/null, especially so that we don't throw a null pointer exception if we try to call equals on null. Otherwise, we're fine. Java's equals method on Boolean, double, and string have the behavior we want for LOX. And that's it. That's all the code we need to correctly interpret a valid LOX expression. But what about an invalid one? In particular, what happens when a sub-expression evaluates to an object of the wrong type for the operation being performed? Runtime errors. I was cavalier about jamming casts in wherever a sub-expression produces an object and the operator requires it to be a number or a string. Those casts can fail Even though the user's code is erroneous, if we want to make a usable language, we are responsible for handling that error gracefully. It's time for us to talk about runtime errors. I spilled a lot of ink in the previous chapters talking about error handling, but those were all syntax or static errors. Those are detected and reported before any code is executed. Runtime errors are failures that the language semantics demand we detect and report while the program is running. Hence the name. Right now, if an operand is the wrong type for the operation being performed, the Java cast will fail and the JVM will throw a class cast exception. That unwinds the whole stack and exits the application, vomiting a Java stack trace onto the user. That's probably not what we want. The fact that locks is implemented in Java should be a detail hidden from the user. Instead, we want them to understand that a locks runtime error occurred and give them an error message relevant to our language and their program. The Java behavior does have one thing going for it, though. It correctly stops executing any code when the error occurs. Let's say the user enters some expression like 2 times 3 over negative muffin. You can't negate a muffin, so we need to report a runtime error at that inner minus expression. That in turn means we can't evaluate the slash expression since it has no meaningful right operand. Likewise for the star. So when a runtime error occurs deep in some expression, we need to escape all the way out. We could print a runtime error and then abort the process and exit the application entirely. That has a certain melodramatic flair, sort of the programming language interpreter equivalent of a mic drop. Tempting as that is, we should probably do something a little less cataclysmic. When a runtime error needs to stop evaluating the expression, it shouldn't kill the interpreter. If the user is running the REPL and has a typo in a line of code, they should still be able to keep the session going and enter more code after that. Let me check the time here. Okay. So I'll probably read a little more and then pick up next time. Detecting runtime errors. Our tree walk interpreter evaluates nested expressions using recursive method calls, and we need to unwind out of all of those. Throwing an exception in Java is a fine way to accomplish that. However, instead of using Java's own cast failure, we'll define a lock-specific one so that we can handle it how we want. Before we do the cast, we check the operator's type ourselves. So for unary minus, we add check number operand expression.operator right. Code to check the operand is, let's see, if it's a double, return. Otherwise, so it can only be a double. Otherwise, you have this runtime error that says it must be a number. When the check fails, it throws one of these. Runtime error, and then you attach the token where it messed up. Okay. Unlike the Java cast exception, our class tracks the token that identifies where in the user's code the runtime error came from. As with static errors, this helps the user know where to fix their code. We need similar checking for the binary operators. Since I promised you every single line of code needed to implement the interpreters, I'll run through them all. Okay, yeah. So yes, these all need to be doubles. So it'll just check that both of the operands are doubles. The last remaining operator, again, the odd one out, is addition. Since plus is overloaded for numbers and strings, it already has code to check the types. All we need to do is fail if neither of the two success cases match. Okay, so they will. Wait, he didn't say the code yet, but this
No,
is
so he replaced that break statement that I talked about before with this statement, the throw.
okay, yeah. That gets us detecting runtime errors deep in the innards of the evaluator. The errors are getting thrown. The next step is to write the code that catches them. For that, we need to wire up the interpreter class into the main locks class that drives it. Okay, that feels like a good stopping point. So I will stop reading there. I will remember that we are at this section.